Hi everyone. So today I'll be presenting the paper from Sparse to Soft Mixture of Experts. This is by Juan Quicksilver, Carlos Gomez, Hassan Sofa, and Neil Holsby from Google DeepMind Zurich. And this is basically their follow-up from their previous work, which was scaling vision to extremely large size. That was basically sparse. In that paper, they just proposed sparse mixture of experts, and it had some issues, and they tried to solve that. Many of those issues in this work. So some preliminaries. Mixture of experts. So this was like probably proposed a long time ago by Joshua Benjo's group, but like in modern times, at least like these two works that this group proposes, they like builds up from this 2017. I think this is the ITL paper by Rom Shazir.
But mixture of expert is an old idea, right?
Yeah, it's very old. But in this idea, they're like it's kind of like re-popularized.
Yeah, Jeff Hinton worked on it for sure.
I think it was like super early.
But maybe even before then.
Yeah. I think it comes from ensemble models and all those work. Yeah. So this is like one work they try to like cite and follow, where basically the mixture of experts is you have like the gating function and another like the experts. So if you have like n experts and the gating function would try to generate or like output n-dimensional vector that will be sparse. So you would like select some experts when you route your input to these experts. So these experts.
I heard Jeff Hinton talk about this. Specialist versus generalist. He gave a talk at NeurIPS 2015-ish. That I'm just like about that. This is an implementation of what he was talking about.
Right? Yeah, I think so. Yeah, I think like I've seen Jeff Hinton's name pop up a lot in the citations. So.
Yeah, also there is a neurosurgeon, a clinician, Elfendon Goldberg at NYU. He has a couple of books published there in my office. So what he is, one of the things that he's talking about is that one of our hemispheres is very kind of randomly connected. Another one is more modularized. And so his idea is probably the same thing is happening. There is an information processing unit that just decides which specialist will address the problem or something like that. So there is like some neurobiological underpinnings for that.
Maybe.
I don't know. Yeah, maybe.
This is like very similar to the pathways model, kind of. Yeah. So yeah, that's like pretty simple. If for the like very general mixture of experts. So we have a gating, it kind of works like a router, and it will route it to the correct expert, or what the model is the right expert. So from there, this group of authors like first proposed like sparse mixture of experts. So this is like mixture of experts, but with like sparsity, and this is. There is like rumor that it is being currently used in ChatGPT 4 for their implementation. Although like OpenAI wouldn't say that, but there's like lots of rumors that this is being used by ChatGPT. So
this approach,
yeah.
Oh, you mean it is a mixture? Yeah.
So what this allows is like this would allow your model to be like scaled insanely high to insanely like high amounts of parameters, because like
at the time only a few things are active, right?
Right. Because you would only like activate like certain parts of the model. So basically like Okay, so if you look at the MOE block, so, and this is the VIP block, so this is only for the, when Google did this research, they only applied with the VIP block. So there are like some doubts or limitations of how to like carry this over to the decoder of the transformer, but in the original work they do it with the VIP, and what they do is like they would change these MLP blocks into sparse MOEs. So not all the VIP block MLPs would be replaced with the sparse MOEs. I think they only like replace half of the MLP blocks in the model. So if there are like 8 transformer blocks, they would only replace the MLP blocks of the last last 4 layers with like sparse MOEs. And what this sparse MOEs is basically these MOPs expanded parallelly into like 4 or 16 or 32 like experts instead of 1 MOPs. And these MOPs would lie on different physical devices or like GPUs or accelerators. So what would happen is like if on different devices, you would have different images coming in, and those image patches from each image would be scored by a router that they train. So this router would then route that image patch from say on this image to a different device, and from this image to different device. So like each of those experts would kind of learn to focus on like certain image patches or certain types of image patches. This is like very similar to like how convolutional filters learn learn to like focus on certain.
Oh, so like a matching filter? It just like, does it react or not react on that?
Kind of like it learns to like focus. There's like a good image that the paper shows what they learn to like what each expert learns. So I'll move on to that. But yeah, like so with this approach, like what you have is like you have sparsely activated devices. So you might have like lots of experts on lots of devices, and with the original sparse mixture experts, they will only activate like some of the MOPs. So only like certain, they would like only activate certain devices, like physical devices. That would result in like lots of savings in flops and computation.
I have a question in this. So how does it actually decide which device or router do you have to go to, or is it like a learning process that goes from end to end?
Yeah, it's a learning process. So this is that's where the new paper. So I haven't started the new paper. That is the soft mixture of experts. So,
Well, but like I now woke up, thanks, Mrinal. I have, this is the question that's relevant to what Mrinal was doing, because this is a discrete decision.
yes. So it is very hard to like optimize.
How do they do that?
So they do not like learn it. So what they do is like they do like scoring, but then they do like top K assignments. So top K is not differentiable, but it is like during inference they do top K.
No, okay, what, it's like max pooling, right? It's, in that sense, it's differential, just only different, flow the gradient back to the top K that you chose, and you can do differential sorting.
Right, but yeah, but I don't think you can train it. Can you train it?
Like, you train through max pooling, you can train through max pooling and you can train sorting, well, based on the features, so you can train features according to them, you do differentiable sorting. And then when you select top K, it's like max pooling. You just like.
I mean, I was reading like it is one of the issues they had with this paper that.
No, I'm sure it's an issue. It's a huge
it's
issue.
a discrete operation.
I'm just trying to talk my way through handbrake, so. But I think.
Yeah, so that's how they do it. Like they do like top K and select like the top scored tokens for each router, for each expert. So they have like a score.
Maybe he has more questions. No.
No,
Yeah.
I'm done with the questions for now.
So this is like for the vanilla Sparse short experts. So the way they do the routing is like you might have like some capacity for each experts for tokens. So they would like drop the token, drop some of the token based on the scores that they learn to give to each of the image patches. This is what they call like batch prioritized routing. So you have like a batch of images, and from all the patches in that batch, they would score each image patches and try to route it to each of the experts. And they would like try to guess like what would be the image class. So this actually performed pretty well.
The experts, are they transformers with self-attention?
No, they are just MLBs.
Oh, okay.
So this is like just at the end of after self-attention and after their normalization, this is what they are doing. So yeah, so they would have like a limited capacity, so that would result in like lots of savings, computational savings as well. This is sort of like attention.
But for MLP, an order will matter. The way you how do you or your patches come in a batch, and or like if you concatenate them, then the order you concatenate them matters because your weights were learned
right
in this order, whatever. It's not permutation and sensitive after training.
Right.
But if your router selected the groups at random, say, or like there is what I'm trying to say, there is a correlation, spatial correlation in the doc image.
Right.
And depending on where you take the patches from and give to this MLP versus you give to that MLP, that order will potentially severely affect the performance of that MLP because it already learned a different order or something like that. Or are they batching them? Or are they
they're batching them and they're mixing them afterwards.
like before giving the MLP? So
Right,
they're
yeah.
adding with some weights or something.
Right.
Okay.
And especially like so they like only each of the tokens they apply the expert function like towards like token wise, and then there's like an output of each of the experts, which they then like mix and then try to like learn the prediction outputs. So yeah, so each of the image patches could also be like routed to like multiple experts. If the model like learns to do that, it could do that, and that would like result in like combined inference as well. So wanted to move to like soft MOEs. So in this work, they propose like soft MOEs to like alleviate some of the problems of sparse MOEs. So with sparse MOEs, like one problem was that it was not differentiable, and it was in some scenarios like hard to train because of that, and also it didn't scale well to like extremely large number of experts. So soft MOEs try to like tackle those. The idea of soft MOEs like a bit like weird. So what they do is like instead of routing each of the image patches to like each of the slots, by slots it means like the input to the expert, input patches to the expert. So like in the previous GIF, there were you could see like image patches going to the experts, and some of them were dropped, and like only 4 of them went through. So that's because that expert had 4 slots. So that's how they define slots. So in this work, during the experimentation, they experiment with like a range of slots, and they decide that, hey, it's like, they get the best results with like 1 or 2 slots, and they just go with 1 slot. So that just basically means like one expert processes 1 image patch during like training. So what they claim is that the number of slots doesn't matter. What matters is like slot times the number of slot per expert, because that is the compute allocation. So you might have like 8 experts and 2 slots, or like 16 experts and 1 slot, and it's effectively the same, because experts are basically just slots. So during sparse MOEs, they would route each of the image patches, but with soft MOEs, what they would do is like, they would do linear combination of all the image patches and for each slots. So they would train that experts would have weights, and the weights would be the linear combination. The weights would be used to like do the linear combination of the image patches, and that would result into like one slot. So here you could see that in this in the top right, in the soft MOEs, they're doing weighted average of a bunch of like image patches, and that is going to like one of the slots in expert. So they're hoping that like for one of the experts, they would learn to have like meaningful weighted average of like certain area of the image, and the expert would try to focus on that. So that alleviates the problem of token dropping, like where you'd have like limited expert capacity, and some of the tokens would be dropped. But here, that would never happen, because all of the experts would always have all of the tokens, like something a combination of all of the tokens. So this is like the soft MOE architecture, and overview of it. So I might come back to this, to be honest, but
Yeah, you already need to come back to it. It's just too dense. But can I ask a question?
yeah.
Sparse MOEs, the word sparse, I understand what we mean, and I understand that they only activating few experts. That's how we say,
Right.
etc. How do you manage to activate just a few experts here?
Yeah, that is actually like, I have been trying to find that answer, to be honest. Like, I totally don't get it. I have tried to find that answer from the paper and from the previous paper. From the previous paper, they did like, okay, with this, basically what they do is like soft assignment, that is just softmax. So, I mean, like, if we somehow at some point don't do hard, like, even if it's softmax, even if you have like 2,000 experts, if we don't like select some experts, like even after soft max, we should be doing like some sort of hard thresholding. They don't say that in the paper, to be honest, but they claim like it's super fast, like from the experiments. But in the previous paper, they say that. So this is not a published paper, by the way. This was like put on archive on August this year. So maybe it's missing, maybe I'm missing something, I don't know. But
Okay,
it's
sorry.
a question
I had
have.
to ask. That's good. Go ahead.
Yeah. So yeah, so let me just first go over like in high level what they're doing is, in high level they have like all the tokens are incoming, and they have like per slot learnable parameters, which they call like phi, or phi, however you pronounce it. So with that, like, so this is like very similar to attention mechanism, but very like close to it, but not really. So they kind of do like pairwise similarity score between the tokens and the slots. The slots are parameters, by the way. So like they have these are like d-dimensional parameters as well, and the tokens are d-dimensional as well. So you have like a pairwise similarity score between the token and the slots, and that's what you have as your per slot learnable parameters. And then you kind of like do a soft max over the I think the slots, and then you do a linear combination of the tokens based on how relevant each of the tokens are to each of the slots. And that's what gives you like a slot linear combination, which you then put into like each of the experts. So the experts are basically MLPs, and they would output like the slots. The dimension is preserved. But next, then you have like the same weights, which is the soft MOE weighting lodges in the top. And this time you do a normalization across the tokens instead of the slots. So you have like the relevant of how each of the outputs are more relevant to each of the tokens. And then you do another weighted combination of the output to regenerate like each of the tokens in a different space. So the first weights that we saw were the dispatch weights, which they call the dispatch weights, and the dispatch weights are basically like as I said, it is like the input tokens times the parameters they have for each of the slots and the experts. So the slots and the experts are n times p dimensional, which is like n is the number of expert and p is the number of slots. So basically that's why they say that it doesn't matter how many slots you have per expert. So you can always have like more experts and less slots, and you can just have like one expert per slot and just be done with it. And that would be your like phi matrix. Sorry, and you would just then compute the pairwise similarity score between the input and that expert weights, and you would get like this dispatch weight from that. So this is like a softmax over that. So it will always be between 0 and 1, and that is why they also like call it like a convex combination of all the dispatches.
I think convex combination is that second line. X tilde.
Yeah. Yes. Because like the D's have already been like normalized. So you have like the 0-1 convex combination within 0-1. And so each of the rows of the expert, each of the rows of that X tilde are then fed into like the expert functions. So I'm not quite sure why they have the floor function here. Maybe this is how they are getting the sparsity. So they have like, this is the ith expert, and P is the number of slots. But yeah, so they do like feed each of those X tildes into the expert functions with the MLPs, and then you get the YI outputs. And each of those outputs are again made like a convex combination with the original D dispatch weights, but instead of the dispatch weights, we have like combined weights because we're doing softmax along the tokens this time. So we have like a similarity score between the outputs and the tokens this time, and they recreate the outputs from this whole like process. So this is how they are like softly routing the tokens through the experts and getting like a output from the mixture of those experts. And here they're not using any sort of like top K like they used to use before. Instead, it's all just weighted convex combinations of the tokens and the outputs of the experts. And they preserve the dimensionality, like going from MLP.
So each expert gets a mixture of everything corresponding to that.
Correct.
expert.
Yeah.
And then, yeah, like, all of them are working.
Yeah, all of them are working, that's my thing as well,
Yeah.
like, all of them are, so I would assume like the outputs of the, like, when they do the outputs, they have like, some experts which learn to more, but I can only see it like, performing better in inference time, to be honest, not during training time. But yeah, this is how they're doing it. So in the paper, they claim like some of the properties of sparse MOEs, and they claim that differentiability is one of the main things, and which they attribute to the like easier training of soft MOEs in their experiments. So all like in the original like MOE algorithms, the core was like an assignment problem between the tokens and the experts, and that assignment problem was basically done in one of two ways. One of those was like token choice, and the other was like expert choice. So in token choice, what they did was like they would take the top K token for each of the experts and route those to those experts. So that was the most popular approach, and I don't know if that's what's being used in the large language models. The other one was like the expert choice, where the expert would have like a particular capacity and say some buffer, and they would choose all of the tokens, which tokens to come. So this was another way. There are like more sophisticated ways, like you could solve, cast this as an optimization problem and like solve like linear programming. People have used optimal transport and also like reinforcement learning to solve this, but those are like more costly or like complicated. So for the two popular choices, there are some issues. For token choice, it suffers from token dropping, where you would have like more tokens trying to go to like each of the experts, and the buffers would be like full. So you would only have the highest scored tokens going to each of the experts. Also, there might be like unbalance, where like many of the tokens from the batch would try to go to the same experts, and the buffer would already be full, and the rest of the tokens would be dropped. So this would obviously have detrimental effects on the model performance. So token choice had those issues. Expert choice only suffered from token dropping. It didn't suffer from like the other issue of expert unbalance, because it got to choose which tokens it could select. So you will always select the number of tokens like our expert equal to the buffer it had. But like soft MOE is like sidestep both of these issues by not having to have like set amount of tokens go to each of the experts, because you always have like linear combinations of tokens going to all of the experts. So yeah. So the authors mentioned
I love your figures.
yeah, so the authors mentioned like some of the limitations. So one of the limitations is that soft MOE is like merging. I think Sergey was also pointing this, like it's merging all of the tokens in the input. So I mean, you do not have the causality between the past and the future tokens. So it's like all mixed together. So it would be hard to like do this outside of VIDs where you're using like a transformer decoder. So I don't know, like some of the blogs people will say that maybe like OpenAI has solved this, but we don't know. The authors mentioned that causal mass, like they do in the attention layer, could be used, but then like one has to be like careful not to introduce like correlation between the tokens and the expert. But I don't know, like I think like even
why is that dangerous? What we want experts to have kind of, okay, this is the kind of correlation tokens that this expert is good at. So you want to, or which?
Yeah, I mean, I would also assume like, we would want to have like some sort of, like some of the attributes of the images should be like correlated with the experts. But, I mean, they say that they don't want like correlation between token and SWOT indices.
Hmm.
Since this would bias which token indices each expert is trained on. I think it's the indices, not the tokens itself.
Kind of not the semantic content of a token.
Not the semantic
but
position.
just location, yeah.
Right. Maybe like some.
Which is also useful. I mean, I
Yeah.
don't know, yeah.
Yeah, but I don't like in batches, like does the positions matter as much because it does like in a batch of images, does the positional information encode the spatial information from the image itself?
Well, but then when you're talking about shuffling, we're coming back to Pavel's results about, they just have stronger, what they do is create, say, stronger regularized models, and that's why they're better.
Right.
Because they kind of
Get rid of.
deprive them of that position and every time reshuffle it differently, et cetera, so.
Right. So yeah, I mean, one of the limitations they are saying is that auto-recursive decoding would be one of that, and the other is like obvious, it's large memory for the frame because you have like so many MLPs, you gotta have them somewhere. So it's a pretty large memory footprint for this model.
Well, but then, yeah, it's not sparse anymore, so
Yeah,
it's back to the beginning, the same,
Yeah,
mm,
so my guess is that they are doing like some sort of routing on top of the soft assignments. Like maybe some of the experts are don't really like focus on very high linear combination or their outputs are not relevant, but then you would need to wait for the outputs.
mm. No, still, like, it's unclear to me what they're doing in order to stop select.
Right.
But yeah, you're going to interpretability.
Yeah, so they, in this figure, they show like some of the experts and what the linear combinations, the weights, learn to like do. So you can see that some of the experts focus on like the faces, the bill of the duck, or like the head, or even the background in the expert 8. So the weight that the expert learns for the linear combinations is kind of like attention, I guess. Which shows that their model is working. At least that's what they think.
That's interesting.
But some experts focus is not interpretable, at least.
Yeah, I think they cherry picked. They say that
Yeah,
there were like thousands of experts in the model. I think so 128 experts in this scenario. So it's only 8. And they also said that it's cherry picked. I think the others might not be that interpretable. Maybe.
Yeah.
So their results are actually very, very good. So, so in this experiment, so they trained like 160 models on GFT 4 billion, like the internal data set. So it's insanely large data set. And they train like small VIP, small 32, small 16, base 32, base 16, large 16, and huge 14. And in all of the experiments, they use the term that it dominates the VIT and the sparse MOEs. For the soft MOEs, the plots are in blue, and the expert choice is in orange, the token choice is in green. Those are for sparse MOEs. And the red is for dense MOEs, and their model is like clear of the Pareto frontier of the other models in time in terms of like the training time and precision. So they also like train the models for longer than usual. So they overtrain the models and they see that it still even in the overtraining regime performs much better in the ImageNet 10-shot accuracy. So for ImageNet 10-shot, they pre-train the model in GFT 4 billion and they train on ImageNet with only 10 examples from each class. So this experiment is basically their performance in fine-tuning to like ImageNet dataset. And it performs much better than vanilla BITs in all of the regimes. So this is an interesting one where they have VITs, soft MOEs, and soft MOE long. So the lightly shaded blue line is soft MOEs, and the deeper blue is the soft MOE with long. What they mean by long is that they do a learning rate cooldown. So they would train the soft MOEs, and then they would cool down the learning rate, that is linearly scale down the learning rate to 0 for 500,000 more steps.
So the difference is they use different models, right? Different size models.
Right. So each of the first dot is basically a VIT small. The second like marker is base 16. The third marker is large 16, and the last marker is huge 16, huge 14. So what you could see is like with the small 14 of the long models in each of these graph performs in terms of accuracy much better than even the like soft MOE B16 in all of the
And what
graphs.
is the difference? Like the number of parameters
It's just
is the same?
Everything is same. It's even soft MOEs. So what they're showing is that it's like soft MOE is very suitable for overtraining to get like much better accuracy than the next larger model. So if you have like a soft MOE, it's always better than VIT. But if it's a soft MOE that is small 14, that is overtrained, then it performs much better than.
That reminds me again on Pavel's results. And I don't know where Noah is, like when you put the self-attention on the top, when you sum everything up and then make a MLP prediction.
Right.
His model also tops the charts of vanilla models. And yeah, you have specialized models that are as good, but they're much more complicated.
Right. Yeah, so they like also make a claim that with overtraining, you can just have like a smaller model perform even better than like the next one or even two like larger models.
Well, but then back again to you, Pavel, that means this is just classification. Possibly we can manually create a feature set that logistic regression will be as good as anything because there is a feature set. They are discovering that feature set. So we just don't know what it is.
Yeah.
And et cetera, et cetera. Yeah. Okay. Interesting.
And this is basically like scaling the experts. So this is one of the problems they're solving here as well. Like in the previous expert choice and tokens choice, the sparse MOEs, the issue they faced was scaling like to very high number of experts. And they said that one of the prime reason behind that was because of the top K choosing and the sorting, which became like computationally more demanding as the number of experts grew. So since they don't have this sort of computation in the soft MOEs, they were able to like scale the number of experts to even 4,096. But it is like pretty clear from the figure that for expert choice and tokens choice, you have like a certain optimal number of experts above which you just like lose performance. So yeah, I think that was the presentation. If you have questions.
Yeah, thank you. That's very interesting and very nice. I have if no one is ready, a random question.
Yeah.
Why did you choose the paper?
This paper. Yeah, I found it interesting, and I actually met the authors in IPR, so I tried to like see what they were up to.
Yeah, yeah.
And I found actually like I thought the original sparse mixture of experts was a very unique idea, like for sparsity research.
Yeah, I don't, any questions? I have comments, lots of comments. Anyone? Yeah, like they have interesting, it's a comment from Reynal, or I'm speaking for him. They have an easy problem, right? When they select the patches. The patches are direct input to the MLPs in the devices. So the gradients in principle can go back, it's the same model. And yet they're having trouble. And Reynal's problem is much more difficult, is that the model does not produce an input. It makes a decision which trigger to pull. And then a process is started that has its own input and stuff like that. So we were struggling with how to solve that, and finally went with reinforcement learning, because Reynal wanted to suffer a little bit, and yeah, I guess. So, but I wonder, why is this problem also hard? Like, our problem is much harder.
Yeah.
It's just interesting. A comment, it's not a question. Yeah. So, no questions, then we finished 12 minutes or way earlier today. There is another talk starting next door in 12 minutes as well. We will stop the recording there. And yeah, okay, well, I want to congratulate you on expert use of DALL-E 3.
Yeah.
But that's what it's for. It's to generate good illustrations and things like that. So it's
It was fun.
yeah. Thanks, and thanks everyone for joining. Unless people online, do you have questions?
Yeah, but for some reason, DALL-E has some problems with number of letters.
That's actually very true, yeah.
Sometimes, not
I
always.
think like I was having trouble like generating images.
No, but images are fine. Text is a
Like
problem.
here they messed up the K.
No, but come on, it's the only model that can do text.
Yeah.
Try me Journey, and then you're like,
But yeah, I mean, it's not bad.
yeah. Oh no, I was surprised at all that it does text.
It's
just like I'm.
DALL-E from OpenAI.
Yes.
It's like now it comes from with ChatGPT 4.
Well, the good part that comes from ChatGPT 4 is that I can throw at it my handwritten notes,
Yeah, right.
and it generates LaTeX.
Oh, does it?
Whatever. If you want, I can ask it
I
to
didn't
generate PostScript or PDF. It's a language.
Yes.
I didn't try that. I'm sure it will generate PDF. It's a type-based language.
Yeah.
Not a PDF, but a text. I will put it in, it will be a PDF. Yeah, but I want LaTeX so I can edit it. And the only thing is that I get carried away and my written text was like long because my notebook is infinite. When it became too long, it just thanked me and like, I'm ready to your questions. I managed to overload it. But it's really great. Well, anyways, thanks for the presentation, and let me stop the recording. I have too many buttons on stop recording. Yeah.